Okay, let's continue. So I'm looking now at another example here. Have 1 minus 2, 0, minus 1, 1 minus 2, 0, 1, 1. And I don't have any smart ideas about this, so I do it the hard way. And the hard way is to compute this determinant here. Well, I should write it down. A minus lambda times E. And this will give me the characteristic polynomial. And it will be the determinant of 1 minus lambda, and then minus 2, 0, minus 1, 1 minus lambda, and then minus 2, and then 0, 1, and 1 minus lambda. Okay, I have a 0 here, so I could make an expansion along the last column, and this will give me 1 minus lambda, and then the determinant of this submatrix here, that is 1 minus lambda, minus 2, minus 1, 1 minus lambda. And then I have this one here, and it will give me minus 2, or I should calculate plus, minus, plus, minus. So I have minus, minus 2, that is plus 2. And then I have to take out this one, and this one, and then I get 1 minus lambda, minus 2, and then I get 0, 1. So this one is 1 minus lambda times 1 minus lambda squared, and then minus, minus 1, so that will be minus 2. And then here I get plus 2 times 1 minus lambda. Now I multiply this in, I get 1 minus lambda cubed. And here I get minus 2 times 1 minus lambda, and here I have plus 2 times 1 minus lambda. Yeah?
Can you see the minus 4 at the end of the
I
times 1 minus lambda? For like for the determinant at the very end, the last one, it's 1 minus lambda times 1 minus 2 at the
So when I do this, I have this value here, and then I take out this one and this one, and I think it becomes that matrix. It's okay. But this is it. This is the characteristic polynomial. Yeah.
The second determinant, the bottom left value is positive plus.
No, because I said I did it after the last column. I could have done it along the first row, but if I do it here, I get minus 1 here from here. This was not the best way to do it, I guess, but so it's completely factorized. And you have that A has only one eigenvalue and the E value is equal to lambda equal to 1. And you have that the algebraic multiplicity is equal to 3. So let's try to find the eigenspace. And here I have to solve this equation, where I put in my lambda value, and this is 1, so I get, if I write down the augmented matrix, I get, if I put in lambda equal to 1, I get 0, minus 1, 0 for the first column, and then I get minus 2, 0, 1 for the second column, and then I get 0, minus 2, 0, and then for the right-hand side I get zeros. So this is the augmented matrix. Now you see, if I multiply this by 2 and add it to this one, I get all zeros. And then if I swap these two rows here, I have, no, then I swap these two rows and I put the 0 at the bottom. I can get the trap T, the totally reduced matrix as. Also, I change the sign in this, so I get 1, 0, 2, 0. And then in this one, I get 0, 1, 0, 0, and then all zeros at the bottom. So what I'm left with is that if you interpret this as equations, then I have V1 is plus 2 V3 is equal to 0, and then I have V2 is equal to 0. So you see you're left with one free parameter. And this means that the solution is equal to your parameter. And then this is 0. And if you choose V3 as a free parameter, you have a T here. And then V1 will be minus 2. And you have that E1 is the span of this vector, minus 2, 0, 1. The geometric multiplicity is the dimension of the eigenspace. This is the eigenspace. It only has one vector. So the geometric multiplicity of 1 is, or I should write, equal to 1. And I could also write that this is the dimension of the eigenspace, or the eigenspace just like this. And now this is clearly less than the algebraic multiplicity of 1. And this means that this matrix cannot be diagonalized. You cannot find 3 linearly independent eigenvectors, and so it cannot be diagonalized. Now I'm going to give you a theorem. Not with this one. And this will be theorem 4. You have always that the sum of the algebraic multiplicity is equal to n. That is, if you take all your eigenvalues, the different eigenvalues, and then you sum the corresponding algebraic multiplicity, then you get n. This is due to the fundamental theorem of algebra. The eigenvalues could be complex or so, because you have this real polynomial that you are going to solve, but this is indeed the case. But if the sum of the geometric multiplicity is less than n, then A cannot be diagonalized. Diagonalized. Now, let's look at yet another example. You have here, and I should press this one. You have here 2, 0, 0, 1, 1, 2, 4, and in this case, the characteristic polynomial is given. And it's minus lambda minus 2 squared you could compute that, but now we assume it's, or we say that it's given here. And you can immediately read the eigenvalues because it's completely factorized, this polynomial here. So you get that lambda 1 is 2, and it has the algebraic multiplicity equal to 2. There's 2 factors. And then the second eigenvalue is 3, this factor here, and you have the algebraic multiplicity is equal to 1. You can always check that you have calculated it. It's not that difficult when you only have 3 factors, but if you sum it up, it should be equal to the dimension of your matrix. It's a 3 by 3 matrix, so. Now, let's try to find the eigenspace here corresponding to the eigenvalue 2. So the problem is to find this eigenspace. And again, I can immediately write down the augmented matrix. I have to subtract the eigenvalue 2 from this matrix. I get, for the first column, I get 0, 1, 0. The second column, I get 0, minus 1, minus 1. For the third column here, I get 0, 2, 2. And then I have the right-hand side, like this. I have a 0 here. What can I do about all this? I can change sign on this, and then I can add it to this one. Then I get rid of this one, and then I can put the 0 at the bottom, and I get the fully reduced matrix as 1, 0, 0, 0. This is, and then 0, 1, minus 2, 0. This is a change of sign on this, and then I put the zeros at the bottom. This one comes from the fact that when I have changed the sign here, I can add it, and they disappear, and I have this row here. Again, you can solve this equation. You get, from the first equation, you get that the first coordinates should be 0. And from the second equation, you get V2. And if I put this on the right-hand side, I get 2 V3. So V3 is a free parameter. And you get that V1, V2, V3 is equal to some parameter times 0 and 2 and 1. And this means that I should write here t is a real parameter. So E2 is equal to the span of 0 to 1, this vector here. So the dimension of the eigenspace, the dimension of E2 is equal to 1, and this is less than the algebraic, and this is the geometric multiplicity of 2, and this is less than the algebraic multiplicity of 2, and this means that this matrix here cannot be diagonalized. So a couple of theorems. So this will be my theorem 5. For every lambda, we have that the geometric multiplicity is less than or equal to the algebraic. You know this because, say this is less than 2, but what if the geometric multiplicity of the other value here is 2. Then you're still home free, but it cannot be, because the geometric multiplicity is always less than the algebraic multiplicity. Also, you can show that this is always greater than or equal to 1. Because there's always an eigenvector, even though you have the algebraic multiplicity of 1. And this leads to the last theorem I'm going to show you today. And this says that if only 1 lambda exists with a geometric multiplicity that is less than the algebraic multiplicity, then A cannot be diagonalized. That is, if you have a problem and you are asked to find out, can this matrix be diagonalized, then you take the eigenvalues and you count the algebraic multiplicity, and whenever that is greater than 1, you check the geometric multiplicity. And if you find one where this is the case, then you can answer your question in the negative. Okay. One final example. I'll hurry with this. A is equal to 1, 0, 0, 0, 0, 1. Now, the determinant of this one is minus lambda. Oh, it should be minus 1. Is the determinant of 1 minus lambda, 0, 0. And then if I interchange these two, I can do that. Then I get 0 minus lambda, 0, and then, or 1 minus, or 1 plus lambda, sorry. And then I get 0, 0, 1 minus lambda. Or perhaps I should have written that originally, but I interchanged these two rows here, and I get this one. And what I can see here immediately is that this is 1 minus lambda. Yeah. Let me do it again. 1 minus lambda, 0, 0, and 0, and then minus lambda, 1, and then 0, and then minus 1, and then minus lambda. So what I do here is that I I do an expansion along the first row. So I get 0, 0 here, and I get then the determinant of minus lambda 1, minus 1, minus lambda. And I get 1 minus lambda. And then I get lambda squared and minus minus 1 times 1. So I get lambda squared plus 1. I can immediately, because it's factorized, I can write down the eigenvalues. I get lambda 1 is 1, lambda 2 is I, and lambda 3 is minus I. Here I have to use complex solutions to this equation here, and you see, I have 3 different eigenvalues. That means I have 3 different or 3 linearly independent eigenvectors, and then I can diagonalize it. And I can check it. You see, the trace here is 1, and if you take the sum of the eigenvalues here, you get 1 plus I minus I, which is equal to 1. So the check is okay. So have fun with the exercises, and don't forget to do the weekly test. Okay, see you.